Dear friends, in last lecture we discussed about the numerical of exercise 9.1, 9.2 and 9.3. Now today first we discuss about the illustration 9.4. That is quite lengthy because in 4 position of a person we have to find out the speed of an image experienced by the person. Okay. Now, first we discuss about what is the question, that is the illustration 9.4. Now, suppose we are sitting in a parked car and we are observing in side view mirror of a car, a person is moving towards the car from the back side. The speed of the person is 5 meters per second. Now, we have to find out what is the speed of an image shown in mirror by the person. At different position of a person at 39 meter, 29 meter, 19 meter and 9 meter. First again, understand this situation. We are sitting in a parked car. We are observing or we are viewing in a side view mirror. Having the radius of curvature is 2 meter. Now listen, in a side view mirror there is a convex mirror, not a concave. And due to that reason, the radius of curvature is 2 meter and focal length is positive, that is the 1 meter. Now the person sitting in the car viewing or the seeing another person moving towards the car with a speed of 5 meter per second. So what is the speed of the image shown by the person in a mirror when the person coming towards the car is at position 39 meter, 29 meter, 19 meter and 9 meter. For that purpose, first we have to use the mirror formula, and on the base of this mirror formula first we find out what is the distance of an image. From mirror formula, one upon f is equal to 1 upon u plus 1 upon, from this 1 upon v is equal to 1 upon f minus 1 upon u. Therefore, u minus f upon fu. Therefore, v is equal to uf upon u minus f, that is the equation 1. Now the speed of a person is 5 meter per second, therefore the distance traveled by the person in 1 second is 5 meter. Already we discussed about the focal length of a convex mirror. Okay. Now first, for u1 is equal to minus 39 meter. That means the jogger or the running person is at position 39 meter from the car or the mirror. At that time, what is the image distance? For u1 is equal to minus 39 meter, image distance is v1 is equal to f u1 upon u1 minus f. F is 1. u1 minus 39. Here minus 39. And minus 1. Therefore, 39 by 40 meter distance. Okay. After the 1 second, after 1 second, the distance of a person from mirror is, that is our u2. u2 is equal to, initial distance is 39 meter. Now, speed is 5 meter per second, therefore distance traveled in the direction towards the mirror is 5 meter in 1 second, therefore plus 5 meter, therefore minus 34 meter distance. And image distance v2 is equal to, again this equation, f u2 upon u2 minus f. F is 1, u2 minus 34 upon minus 34 minus 1. Therefore, 34 upon 35. That is the distance of a person when or after 1 second. Therefore, what is the speed of image? And speed of an image after 1 second. So we know that the speed is equal to changing position or the changing distance upon total time interval. So initial distance of the image is v1 minus v2 upon v1 is this 39 by 40, 39 by 40 minus v2 34 by 35 upon total time interval is 1 second. Therefore, 39 upon 40 minus 34 upon 35 so is equal to 1.280 meter per second. That is the speed of a clear? So where is it quite lengthy? There is only the answer for the initial position u1 is equal to 39 meter. Now, similar way for u2 is equal to minus 29 meter. 29 meter distance. That means when the jogger, that means the running person is at 29 meter distance from the mirror of a car. At the time, what is the speed of the image? What is the speed of a image? Now, second part, when the person is at 29 meter distance from the mirror. At that time, the image distance, that is the V2 is equal to, here we take also 1, okay, V1 is equal to F U1 or U1 minus F. But here U1 is minus 29 meter, F is 1, therefore 1 into minus 29 upon minus 29 minus 1, therefore 29 upon 30 meters. Whether in 1 second or after 1 second, after 1 second, the distance of a person from here is, there is our u2 is equal to minus 29 plus 5 is equal to minus 24 meters. Now, and image distance corresponding to this object distance, that is the V2 is equal to F U2 upon U2 minus F. Using this expression, therefore V2 is equal to F is 1. Now, U2 is minus 24 upon minus 24 minus 1. Therefore, 24 by 25 meter. There is the position of an image after 1 second. Therefore, the speed of an image is equal to, again, V1 minus V2 upon V. V1 is 29 by 30. 29 by 30. V2 is this 24 by 25. 24 by 25 upon 1. Therefore, 29 by 30 minus 24 by 25. So, find out yourself what is the speed of an image. That is the second case. So, the same way we have to repeat for the different value of the position of an object, 19 meter and also the 9 meter. Clear this? Okay, for different value, the steps are repeated only when numerical values are changed. So try yourself. Now for u1 is equal to minus 19 meter and for u1 is equal to minus 9 meter. Distance, find out again the v1 and v2 and also the speed of an image. Clear this? Oh. Okay, after the numerical, this type of phenomena is shown in our daily life. When we see the sunrise or the sunset, we are not seeing or not feeling the sunrise or the sunset at the actual time, because the sunrise is experienced by the us 2 minutes earlier, and sunset is also experienced 2 minutes later after the actual time. For that purpose, they explain the sun is visible before the sunrise and after the sunset or the sunset. For that purpose, first we must be clear about that what is the actual sunrise and actual sunset. When the sun is crossing the horizon, at that time the sunrise, or on this side the sunset is take place. Again, the actual sunrise and the sunset is that when the sun is crossing the horizon. That is known as the actual sunrise and the sunset. Now, the sun is visible for a little before the sunrise and a little after the sunset, because due to the reflection of the light to the atmosphere. That means whatever the ray of the light coming from the sun, so it has to pass through the atmosphere surrounding the earth. Now listen what's happened here. So here the atmosphere, the density of the atmosphere around the earth is not constant. We know that as we go up to the surface of the earth, so the density of the atmosphere decreases. Therefore, the atmosphere becomes the denser to the rare medium. Denser to the rare and rare medium. Therefore, when the ray of the light coming from the sun, so it has to travel from rare to the continuously increasing, that means the denser medium. Therefore, here the reflection takes place, and reflected ray enter in the eye of a person on the surface of the sun. Therefore, the person feel that the rays not coming from this sun, these rays are coming from this sun. So there is the apparent position of the sun, and there is the actual position of the sun. Therefore, we feel that the sun is rise, but actually the sun is not rise. Sun is not rise. Okay. So what is the time difference between the actual and apparent sunrise? The refractive index of a medium with respect to the vacuum is, that is the 1.0029. That is the refractive index of a medium with respect to the vacuum. And corresponding apparent shift in the direction of the sun. That means how much the apparent shift is obtained in the direction of motion of the sun is 0.5 degree. 0.5 degree. Now, the time taken by the sun for displacement of 180 degree, that means from this to this position. 180 degree, the time taken is 12 hours. 12 hours multiplied with 60 minutes, so that much minute. So 12 into 60 minutes. Therefore, what is the time for 0.5 degree displacement? For displacement of 0.5 degree, the time is what? Therefore, T is equal to 12 into 60 into 0.5 degree upon 180 is equal to approximately 2 minutes. Thus, the time difference between the actual and apparent sunrise and the sunset is of 2 minutes. Therefore, when we see the sunrise is 2 minutes earlier than the actual event of the sunrise. And the same way, when the sun is set, after the 2 minutes later, we can see the sun. Here is, that is the due to the phenomena of refraction by the atmosphere. And after that, we are going to start our discussion about the total internal reflection. Okay. Now, phenomena of total internal reflection. This phenomenon of light is important in our daily life, because in communication system we are using the total internal reflection in optical fiber. We also discuss about that in uses of total internal reflection. Now, first, what is the total internal reflection? Up to this, we discussed about the phenomena of reflection and refraction. At the time, we only consider the oblique ray incident on a surface, right? But no, here any ray incident on the surface separating the two medium, it is partially transmitted and partially reflected. That means the both phenomena of the reflection and reflection take place at the same time for all type of the light rays. If the light rays is incident on the surface, normally in that case also the partially reflected and partially reflected or the transmitted in the mirror. First thing, when the light enters from an optically denser medium to the ray medium, so it interface, it experiences the partially reflected and partially reflected in the same direction and partially reflected in other medium. Again, what's happened when the light enters from optically denser medium to the ray medium? So at the interface that means the surface separating the two medium, it partially reflected and partially reflected. Okay. Now remember this figure. Here the two medium, one is the A as a ray medium and here the water is our denser medium. Here we take the A is a point source or the point object, that is actually the light source of the electric bulb we placed in this denser medium. Okay. Now, as shown in the figure, A is a point object of the light source in a denser medium, where the effect index N1 is equal to N. And now, the rays we consider AO, AO1, AO2, AO3. These rays are partially reflected and partially reflected at the point O, O1, O2 at the surfaces. Clear? So what is shown in the figure, we have to describe this thing. In figure A, the point object or the light source, here we consider the rays AO, AO1, AO2, etc. gets partially reflected and partially reflected at points O, O1, O2, O3 at the interface. Now, from this way, what we say there? Yes, we are going from O to O1, O1 to O2. So, angle of this incidence is going to increase. Here the angle of incidence is this. Here the angle of incidence is quite more compared to this. Now, at point O3, the angle of incidence is again increased than the O2. Therefore, the angle of incidence increases. Therefore, the angle of refraction also increases. Angle of refraction also increases. At particular value of angle of incidence, the refracted ray BC becomes parallel to the interface, that means the surface separating the two medium. Again, for particular value of angle of incidence, the refracted ray moves parallel to the interface separating the two medium. Clear this? Now, on the basis of this, in this condition, this angle of incidence is known as the critical angle. Now, what is the definition of the critical angle? The angle of incidence for which refracted ray, the angle of refraction, refracted ray becomes parallel to the interface. Or in other words, instead of this, angle of reflection becomes 94 pi by 2. Such angle is known as such angle of incidence is known as critical angle, and that is denoted as IC or sometimes only C for the critical angle. Again, the angle of incidence for which the refracted ray becomes parallel to the interface. Or in other words, the angle of refraction becomes the 90 or pi by 2. Such angle of incidence is known as critical angle. It is denoted by IC or C. And what is the refracted ray in this condition? In such condition, refracted ray is known as critical ray. Critical. Now, so there is the phenomena of, sorry, there is the definition of critical angle. Now, what's happened? As we further increase in angle of incidence, that means the angle of incidence is more than the critical angle. Or AO4. What's happened? Here, the refraction phenomena does not take place. Only this ray is 100% reflect back in the same medium. And this phenomena is known as total internal reflection. Again, if the angle of incidence is increases more than the critical angle, so reflection of the incident ray does not take place. But this incident ray 100% reflect in the same medium. This phenomena is known as total internal reflection. Clear this? Now we have the definition of total internal reflection. Now, if the angle of incidence is increases, then the critical angle. If the angle of incidence increases, then critical angle. That means the I is greater than IC. The reflection not take place. And incident ray totally reflected in the same medium is known as total internal reflection. Total internal reflection. Now, what is the definition of total internal reflection? Just we discussed about that the angle, as the angle of incidence increases, angle of reflection also increases. For particular value of angle of incidence, the refracted ray becomes the parallel to the interface. Now, if the angle of incidence is increased, then the critical angle. That means the I is greater than IC. What's happened? The refracted ray, but the angle of reflection is also increased more than 90. More than 90. That means that is the totally reflected in the same medium. So this phenomena is known as the total internal reflection. Now, on the basis of this, we are going to get the relation between the critical angle and the refractive index of the material. So, applying Snell's law at O3 point, this point. Yeah, Snell's law is that N1 sine I is equal to N2 sine R. N1, that means in this medium the angle of incidence takes place, the refractive index of this medium is N1. And the medium in which the angle of refraction is taken, it has the refractive index is N2. Therefore, here N1 sine IC is equal to N2 sine 90. First we write in that form. N1 sine I is equal to N2 sine R. For O3 point, I is equal to IC, then I becomes the 90 or pi by 2. Therefore, in 1 sine IC is equal to into sine 90. Sine 91, therefore, in 1 sine IC is equal to only into. For A medium, into is equal to 1 and n1 is equal to n. Therefore, in sine IC is equal to 1. Therefore, sine IC is equal to 1 upon n. That is the important relation. That's of the relation with the critical angle and the effective index of embodiment. Clear this? So that is the important equation to the total internal reflection. Very easy, only keep in mind the figure so you can attempt yourself to answer this question. Clear this thing? Okay.